score. Paranor gives me the +1 on the volume. Susie brings it in. Fenring. Everybody's happy with the volume, so I'm going to go ahead and bring up my integrated developer environment, which is IntelliJ. I use this, and thankfully, with my university credentials, I get to use this for free. Otherwise, it would be $100 a year that would drain off our CosmoQuest funding. Hey, DPI's got jokes over there. IntelliJ, that's what's up. Anyway, I've been banging a lot of code on this bad boy since last I got to show it to you guys. And so much so that I've just about got Alpha 2.0 functionality completed. Dr. Plazas, or Andreas as we call him at the office, created some simulations for me that I don't think you all have seen. And with those simulations, I've been able to actually discover that my code is a little buggy in a couple areas. And we'll talk about those today. And I see a question here from Fenring asking me how I feel about IntelliJ compared to NetBeans. NetBeans I never loved. We were forced to use it at university. The first 3 semesters of the computer science degree, Introduction to Computing 1, 2, and 3, were all taught in Java. And the first semester, they forced us to use NetBeans. I guess because it was just easier to teach the syllabus material. But the second semester, where we started learning how to compile Java from a command line as opposed to building it from an IDE, we were then given the ability to use any IDE or none that we chose. And it was almost immediately that I started using Atom. And it wasn't quite that early that I used Atom. I can't remember what I used before Atom came out. It was open source, I assure you. Whatever it was open source, lightweight. And then when I discovered Atom, I moved to it. And now Visual Studio Code seems to be taken off with the open source world as well. So I may give that a look, see if I ever get frustrated with Atom. But for now, IntelliJ for this project, and Atom for just about everything else, especially my Python code. The reason I use IntelliJ is this single Java class file so far is what this plugin consists of. The rest of the stuff you see is the IntelliJ code, the source code for IntelliJ that we are building this plugin to work with. And so I just build it in here so I can, if I have a question on how to access the API for this code, I just go look at the class files and stuff instead of in some cases looking up the API. But sometimes I'm not in the mood to review code, and I'll just go to the API website. But anyway, that's kind of my spiel on IDEs. To build the ImageJ code base, it uses Ant as a dependency management tool, and IntelliJ just builds it easily without me having to use command line things, because when I first started looking at this, I understood none of it. So I didn't need more learning curve as far as figuring out how to build it and all that jazz was concerned. I had to comb source code to figure out how to manipulate telescope images. I didn't want to add figuring out how to build ImageJ from a command line to that. I wanted to get some code done and get some functionality. I thought I saw Maven, some Maven something in here, but not that I'm aware of. I'm sure it can, but I haven't seen that dependency management tool in this project as of yet. And I'm trying to remember where the Ant. I know the build XML is part of that, but there was another. I don't know what this is. What is this? Oh. It's the output. I remember when I pulled from the repository, because I'm at my home office today and I coded on this in the Edwardsville office yesterday, and I pulled from my repo. Here, I'll show you what I'm talking about. This null was plus 259 insertions, and I was like, what in the hell is that? But this is the output of an image that it found 259 objects in, so that explains that. We're going to learn together today, folks. Anyway, I need to eliminate that. And then get it out of my... Oh, I guess I closed that terminal altogether. Okay, anyway, so let me kind of show you the new functionality that I've been working on since last time we talked, and we're just gonna open up a very basic zero noise desktop fits images test. This Gaussian fits. It's just an image of 256 very tiny objects on a very dark background with zero noise. And then we're going to tell this that an object is an object when it is 6 standard deviations over the background. And then for now, I was working on a GUI and got kind of stuck and wasn't making any progress. So it was pointed out that maybe I should just go ahead and get back to functionality. Work with console input for now, and then get back to the GUI once I had magnitude, which is our target for the AGU conference we're going to in December. Is we want this bad boy determining magnitudes of objects, and we're close, and I'll show you how close we are here. But for now, and it's going to be hard to see, and I'm not entirely sure if or how I can. Oh, there! It's the same way I increase the font size in the code. It algorithmically calculates a full width half max of those objects. The average full width half max of the objects is 4.047 whatever pixels, and then it gives me the opportunity to update that if I want to change it. We're going to leave it where it is, and then it kind of builds an aperture, an inner and an outer annulus from there, and it chooses 4 times the full width half max for the aperture. I think it goes to 8, and then 10 or 12 for the inner and outer. We'll find out here in just a second. We're going to leave everything, and there's 8 for the inner annulus, and then 10 for the outer annulus. And then it asks us about gain and readout noise. And then, of course, it finds the objects, and then it spits out some useful information for each of those objects. And then, even more interesting is, come on, man, is the image. As you can see, it now places colored, the red is the aperture, the green is the inner annulus, and the blue is the outer annulus. Okay, and then obviously, well, not obviously, because this was all stuff that Pamela and Andreas have been helping me understand. Oh, you know what? You're right. My fan is thumping the microphone stand. My bad. I hadn't noticed that, but hopefully... Unfortunately, doing without the fan is impossible. I would literally melt before your very eyes here. Thanks, Fennerig. I'm kind of proud of it myself. But anyway, the aperture inside this red circle is essentially the light that we're interested in, right? Thanks for hanging out, Paranor. Appreciate you keeping an eye on things for us. I still got Guido, and I think... let's see, who else was in here? Susie was in here with me. I got plenty of help. Plus, it's not busy enough that I couldn't handle any sword responsibilities myself anyway. But anyway, inside the red is the light that we're interested in, okay? Between the red and the green is just some arbitrary distance from that object to avoid capturing any light pollution from that object into this area which we are interested in, the inner and outer annulus. What we're doing is we're measuring the brightness of all the pixels inside this region to gather what we call a background. That background is an intensity that we want to subtract from every object or every pixel inside of the aperture in order to get the true intensity of that object, or the true brightness, or the signal, or nomenclature is not my strong point. If we had astrophysicists in the chat with us here, like Dr. Matt, Dr. Andreas, or Dr. Pamela, I'm sure they'd be correcting me if I was using the wrong thing. But essentially what you need to know is we're subtracting this intensity from all these pixels because even though we can't see it, there are electrons captured in those pixels. There's just very few of them. So we want all those background electrons subtracted from all the electrons inside of here so that we have a truer intensity. And then here, each object, you've got the centers of the objects here. You have the full width, the average of the full width half max across each axis, X and Y. And then this is 1.36 times 10 to the 7th electrons, which is a little high because my understanding is the input on this was exactly 1 to the 6th electrons. So that's one of the bugs that I have to determine. Obviously, this is a simulation that was created. Dr. Andreas knows what the inputs were, so obviously I need to be getting those same outputs out. And then this is the flux, the plus or minus, which is some fancy standard deviation on background signal and readout noise. I could show you it's just a square root of a bunch of standard deviations. And that's essentially where we're at. Now, the other bug, if you'll remember, I mentioned two. The other bug is this is a noise-free image that... shit, I already closed the... Oops, shoot, I mean, I forget. Well, we can use... I think the S word is... I think it's the super dirty words we try to avoid, because... but anyway, I think I closed my text output on this, but if you'll notice, I'm going to run this same simulation on something with a little readout noise, and then I'll show you another bug that I've discovered on top of the measuring the electrons in the image. But real quick before I do that, I see there's a little chat going on, so I'm going to try to catch up here to make sure I'm not missing any questions. Alright, everybody's sending Paranor off, and then DPI is asking if I'm getting a baseline noise level and distribution to filter the true light levels. Yeah, that's I guess a TLDR of what's going on. We are trying to subtract that background, those background electrons from behind that object to slightly lessen the intensity, so we get a more natural, what's the word I'm looking for? It's just the features of light are more natural to the object without anything that might be behinding it pushing light through, if that makes sense. Somebody's making my Facebook make noise. I gotta stop that. Anyway, yeah, Fenring, I gotta be honest with you. When I first started at CosmoQuest, I had a job offer from AT&T that paid a little more than what CosmoQuest was offering, but it wasn't nearly enough to justify many facets of working. One, driving into downtown St. Louis every day instead of downtown Edwardsville, which is 1/3 of the time and commute a day. Two, working 2, sometimes 3 of my days a week from my home office, meaning no commute. 3, enjoying wearing comfortable clothes to the office instead of stuffy, business casual or anything else. I mean, I wear this Rick and Morty t-shirt that I'm wearing now, makes constant appearances at the office, my cargo shorts. It's if you ever went to the Apple bar and see how they dress, we get to dress in similar ways. It's comfort is paramount. When your brain is burning all cores at 100% and all your RAMs being used and your swap drives starting to sweat, comfortable clothing can make all the difference in figuring out a problem or being stuck for unreasonable amounts of time. Pamela, who is a top tier supervisor, does all the garbage work, dealing with all the nonsensical things so we can focus on developing a tool for scientists. So many things that make the difference in the salary that I'm paid at CosmoQuest, and the salary that I'd be paid at AT&T, and not known by more than a dozen people in the building, and working on a project that fascinates me instead of some massive tool that's going to make AT&T even more money than they already make. I'm not interested in that. I'm interested in helping advance science, helping make scientists' jobs easier so they don't have to program. When I tried to be a physicist, I wanted to be an astronomer when I went back to college, when I was 37 years old, and then I learned the hard way that physics is hard, math is hard, and physics, non-PhD physics have an even harder time finding work than PhD physics. And I didn't have time to get a PhD, and then I couldn't handle the math anyway. So I talked to the department chair of computer science at our university. He said to me, hey, come get my degree and code for an astrophysicist and be involved in the science and make a lot more money than you could with a bachelor's in physics. And guess what I'm doing? Guess what I am doing to this day with a great benefits package and a living wage. I am writing code for an astrophysicist, well, more than one, but I report to one as a supervisor, and I couldn't be happier. So definitely have the coolest job, the ideal job, the job that I dreamed of when I stepped into my first day of computer science classes. I'm doing it. So anyway, back to that second bug here. Let me open an image with a little bit of noise in it for you. Desktop, fits images, test, simulations. Okay, so signal to noise, I have 10,000 signal to 1 noise in this guy. And it's probably gonna be tough to see. I don't know, I think I'm streaming in 1080. Let me look at my settings. Let's see, stream output. Video. Yeah, I'm streaming in 1080, so hopefully you can see that. But if you'll notice, the objects are bigger and the background is a little lighter. It's not that jet black. It's just got a hint of gray to it. And what we're going to see here, it's essentially it's 256 images. It's 1, 2, 3, not images, objects. 1, 2, 3, 4, 5, 6, 7, 8, 9. 16 times 16, I believe, is 256. So there should be 256 objects here. And what we're going to find when I run this is that we get a full width half max of 16, first of all, instead of 4. Which, oh crap, I meant to change these values when I run that. We get a full width half max of 16 because the objects are larger in this image than they were in that original image. Let me open that again. I want to change those multipliers of the full width half max, because what happens is if I leave them at default, because that full width half max is 16 instead of 4, you're getting 16 more pixels per multiplier instead of 4. And then what happens is that annulus that we were talking about includes all of the 4 objects around it, which makes the iterations in what's called the sigma clipping, which is something we do to eliminate outliers from that annulus. That sigma clipping takes a lot of iterations to get all those super bright points out of there, and it takes a really long time. And this is the whole point. Oh, shoot, I didn't mean to lose that dialogue. That's the whole point of allowing these multipliers to be changed. I really wish this would load on my current screen instead of my other screen every single time. I should probably research how to figure that out. But anyway, I have to drag them over here so you can see. We're going to leave it at 6 standard deviations. And then, like I say down here, we get a 16 full width half max. We're going to leave that at 16. We're just going to change these aperture multipliers. Instead of 4, we're going to give it 2. 2 times that full width half max. Here, instead of 8 times the full width half max, we're going to give it 3. And here, instead of 10, we're going to give it 4. We're going to leave gain and readout noise at their originals. We're going to let this run. Okay, so here's a hint already. I already told you there were only 256 objects in this image, and my algorithm reports it found 259. And I will explain to you exactly why here momentarily. I think it's still building the overlay for the image, but there's the text output, which if we go down here, you can see here it's confirmed there are 3 additional objects, and I'll explain why. I know why that is. I'm not entirely sure how I'm going to fix it, but I suspect I will be returning to my roots and looking at source code in MStar to solve that problem. Where is my overlay? Maybe I clicked something and it put it. Yeah, it's up. It went behind Windows. So here it is. Here it is again. As you can see, my changing those multipliers has essentially kind of overlapped those outer annulus. It's kind of perfect. Like it's going to grab the least amount of light pollution from the surrounding objects at these radii. And if we zoom in and just get one, now that we're zoomed all the way in, you can sort of see, I think, at least I hope, you can sort of see some of this readout noise around the object, how there's a lot of light gray pixels in this area. Yeah, I can see it on my little tiny screen, so I think you can probably see it too. But here, what we're going to find is, I'm going to zoom back out, and then we're going to go down here. See these very dark circles? It's because my algorithm has found these 2 objects here and found the same object twice. So I'm going to try to sort of describe the way that we determine what images are and how we combine all pixels into a single image to try to help you understand why this is happening. So to zoom all the way back out to the OG image, let me let this take a... No, went to the wrong stinking monitor again. Why are you not zooming to full screen? Deep breaths, Joe. Deep breaths. Deep breaths and a sip of LaCroix. It'll solve my problem. Okay, so what my algorithm does is when it loads the image into memory and it does a little statistical analysis, not quite DPI, not quite. After the image performs a statistical analysis, essentially what it's looking for is an average of the pixel intensities, right? In a non-crowded star field like this, the average is going to be closer to that dark color than it is to the light color, right? So that little dialog then asks, how many standard deviations over that background do you want a pixel to be before we pull it out and say, hey, this thing is bright enough to be part of an object that we want to look at? The standard choice is 6 standard deviations. When you have crowded star fields, you can lower that, and it will help separate the objects. It gets difficult when the light noise from one object permeates a nearby object, and that's when it has a hard time kind of blocking and separating objects. But we will get there, and we will get there with lots of help from astrophysicists who know complex mathematics. But what it does is it scans from the top left corner, it scans each individual pixel's intensity, and if that intensity is 6 times the standard deviation of the background from the background, it's like, okay, we found a pixel that we believe belongs to an object. And then what it does is it scans all 8 pixels around it. And I can't remember which way it starts. Whether it starts to the right or up or starting at the left, I don't think it does, because that's kind of asinine since that's where it comes from in most cases. But I'm pretty sure it may start. I don't know. I could look and figure it out. But anyway, what it does is it scans the 8 pixels around it. Any of those 8 pixels that are also 6 standard deviations over the background or brighter get added to what's called an unidentified object class. And then what it does is it checks to see if any of those 8 pixels are brighter than the pixel it just came from. If it is, it sets that to the new object's center. Okay? That also may be a flaw in my logic, is trying to track center immediately before we gather lots of the pixels, but then it makes that brightest of the surrounding pixels the new center, and it scans it also sets all the pixels that it's already scanned to that background intensity, so they're not caught again. Okay, I forgot to mention that. That's important, because obviously if you move up and right 1 and you scan all 8 again, it's going to scan the one it came from, right? And you don't want that same pixel being put into the object again. So it changes scan pixels that it puts in objects to the background color, and then it just keeps going until it runs out of pixels. Now imagine, let's go in here to one of these objects that it found twice. Okay, so let me try to get this a little more centered. Okay, so let's imagine that so here's the object, and I'm guessing probably somewhere in, like if we're coming from the right, somewhere in this region. Can I? Yeah, okay. So somewhere in this region is going to be that first pixel. Let's call it this one. Let's move that out of the way. Selected the wrong. Okay, well, we're just going to call it that one. Okay, so it grabs this pixel, and then it scans the 8 around it, and then let's say this is the next brightest pixel here. And then it makes this the center, and it keeps going this way. And as it gets down here, it's going to eventually kind of gravitate towards the center, right? Now, let's say it finds this center pixel. And it scans the 8 around it, and this is the brightest pixel. And it pulls all the 8 pixels around it in as part of the object, but this is the brightest pixel, and none of those pixels around it are the brightest. Well, then it's running this recursive call. Once it stops finding brighter pixel, then it returns to the pixel, this guy way up here, where it started, and started tracing its way back down this way, and then continues on the rightward path and just goes again. Now, keep in mind, all the stuff that it's captured has been changed to the background color. I don't even know if it's captured any of this stuff over here, to be honest. I should probably debug and try to... Andreas actually made me some new simulations with one object in them, which will make debugging of this what's called the walk. There's a walk image method, and then there's a find nearby objects method, which runs... what it does is when it finds that first pixel, it's been scanning and it finds that first one. And what it does is before it creates a new object, what it has to do is say, okay, is this pixel near an object that has already been created, right? And that method is where this is breaking down somehow. And I've got to figure out why. Now, I think the first of those two bugs that are the easiest to determine is counting these electrons. Okay, this bug, figuring out why it's doing this, that's going to be, for lack of, well, for me attempting to control my language, it's going to be a real pain in the undercarriage. But it's something that's got to be done. So I'll probably begin with this problem first. And that concludes explaining the 2 bugs that I'll be working on. Well, I don't know if I'm going to get much work done on them because I need to get to the office relatively soon because we have a volunteer coder coming in, and I think we're going to try and sit down with Ryan since Ryan's leaving us Friday as his last day. We're going to try and sit down with him so he can kind of guide us a little bit more on this Django migration that we're doing on the CosmoQuest website. I want to be able to help out if I can while he's gone, and we're waiting on Tanner to get back from his summer internship that he took with AT&T, interestingly enough. But you know, we got to give the kid an opportunity to go explore that corporate environment and see how he likes the difference between working with us and working there. You know, he might find that increase in pay to be worthwhile to deal with the corporate environment. I did not find it so. Okay. Hey, Annie, is there a way to find out you could visually watch the algorithm work on a single input? Not that I can think of. I suppose I could probably implement it creating, and that's not a terrible idea. Well, no, Fenring. Okay, so Fenring brings up a point that as soon as I finish responding to Hanny, I'll show you another one with lots more noise that beginning near the end of the image doesn't necessarily correlate to the problem. There are simulations with much more signal to read out that it just turns into a cluster fornication, we'll call it. But responding to Hanny, that's actually a great idea. Something that I could do is have it create those regions of interest around the pixel that it has as a center, and then have it create the pixels region of interest as it scans them, and just put breakpoints at those places so it goes slowly. And I could do that on the single object simulation. That's a great idea. I think I'm going to use that idea when I get to that point in debugging. Now, to get to DPI's question, let me run my code on one of the higher noise. Well, actually, I might not even have to run it. I think I can probably just show you the simulation output that I sent to Dr. Plazas when I ran them. Let's see here. I don't know why I took that over to the other. I do not need those videos. That is me testing OBS. Get them on my face. Where did I put those? Desktop. Fits images. Tests. Oh, I don't have them. Those are on the box at work. Okay, it's fine. We'll just run it. We're gonna run this bad boy on one of the simulations with more noise. Let's try. I think even the next one. And this one, I mean, it definitely looks gray, and those objects are barely brighter than the noise. I mean, it's clear to see that there's noise here, right? And it's just 1 order of magnitude shyer on the signal. So instead of 10,000 signal to noise, it's 1,000 signal to noise. We're going to give it 6 standard deviations. Okay, so now you see the full width half max is reduced from 16 to 12, which should not be the case because the objects are the same size, I believe, as they are in the other image. I'm going to kind of put that just a smidge off the screen so I can grab it again easily off my second monitor instead of having to use Alt-Tab. But we're going to leave the full width half max alone. We're going to leave, I think I changed that to 2 last time, so we'll just change it to 3 this time, 4 this time, and we'll give it a larger annulus, and we'll give it 6. Leave gain and readout noise. Okay, so look here, 442 objects found. Holy shit, that's too many objects, right? We're supposed to have 256. That's doggone near Double. Now, this thing is chugging. Yeah, for sure. And it's also probably as bright as the object, meaning that it's finding lots of objects that are just single pixels of noise in here. But it still hasn't given me my, there's my output and my overlay are now given. Brace yourselves, you ready? You ready? All right. So look here. Didn't find this object at all. Didn't find this object at all. You know, there's objects here that it didn't find at all, and then there's objects here that it found at least twice. This one was found it looks like 3 times. So as you can see, we have work to do. Let's see here. Which one do you want as desktop wallpaper? Because I will... You dirty thing. Stop. This thing is the strangest, man. Like, I don't understand why that box changes size anyway. I will create as high a resolution image for you as is possible, if I could ever figure this stupid thing out. But anyway, let's just quickly run it on something with lots of noise, and you can see the real mess. I think even the one down from that was the one that it was just completely wild, made no sense. 100 signal to noise ratio. 100, you can barely see the objects at all. I'm terrified at how many objects it's going to find in here. Okay, so this one, look here, full width half max, 0. Actually, it's probably, that's divided by 0, meaning that the y-axis full width half max was 0. Meaning it's infinity. Yeah. Let's see here. So it becomes basically useless at that signal to noise ratio. Actually, I'm gonna try one more time to see if I can. Oh, I know where it's at. It's in Slack. Hold on, I can find that image in Slack. Maybe. If it hasn't fallen off, because we're poor and we don't have founded it. We don't have the paid Slack account, so we have the Slack that dumps our uploads off after like 10,000 of them, which is still quite a ways to go back, considering there's only about a dozen of us or so that use this Slack. So that should be downloaded. Let's see here. Yes. No! Okay. I forgot that was my algorithm trying to open a fits image, not me trying to open a tarball. Let's try this again. Please work. Thank you. And, it worked. It was just a little slow. It's about it's not the... Where is the size of this stupid thing? I don't want to know how much free space I have. I want to know how much, how large the actual 100 megabytes. Okay, so it's not that big. Anyway, SNR. I think. Okay, so there is that's essentially the image that I just showed you. That 1,000 signal to noise. I could have swore, let's see, simulations, 100. Yeah, okay, so I did run that, and there's the 100, and that was the one that was just super random. Now, it looks like it's actually doing a relatively decent job of sort of finding, like, Oh man, this one won't let me zoom. Control plus? Okay, not with my mouse wheel anyway. It's hard to say what it's doing here. But anyway, that, and then obviously 70 was an even bigger mess. And then I think I stopped, and I have lower signal to noise ratio, but I didn't, there was no point in running them anymore because you can just see that all falling apart as the signal to noise ratio goes up. Let's see here. Let's see, DPI, the images it finds are off the grid, gauging from the distribution. I'm not sure what you mean by that. Well, I'm not entirely sure. At anything over, about signal to noise 100, I'm not sure how we'd be able to differentiate objects anyway. But those are the simulations he gave me. Apparently, it's standard fare to test algorithms on images with that signal to noise ratio. So that's what we're doing. Obviously, we've got to perfect that 10K signal to noise ratio first. Once we get there, we can work on perfecting that 1K signal to noise ratio, and then the 100, and then the 10, and so on and so forth until we masterfully perfect it. I'm not sure that's the goal of our tool. The goal of our tool is to help grad students do science and not programming. And then obviously grad students and up, astronomers, scientists of that level of education are having to learn how to program and having to learn how to use cryptic command line tools to do science when they should be focusing on double clicking on an icon and getting their science instead. You know what I mean? That's our goal. Off the grid does not match the pattern. Yeah, okay. Objects makes a little more sense. Yeah. That definitely makes sense. Yeah, it's definitely kind of swerving off the beaten path there when it shouldn't be. If you want to see an interesting image, I'll run you through an actual star field. And then I'm going to, how long have I been live? I've been live almost 45 minutes. Then I'm going to spend a few minutes kind of running you through the code that calculates these electrons. And then I'm going to head into work to meet with Ryan and Anya and our volunteer Python developer and see if we can get any knowledge on the CosmoQuest migration, so when Ryan leaves us Friday, if something crashes over the weekend or next week, we've got a couple of weeks until Tanner gets back, so I just want to be able to help Pamela with that if she needs it. So let's run this. I'd like M13. Let's run it on M13, which is this guy, right? So what we have here is a relatively this is not a dense star field with the exception of that center, right? So we've got an interesting problem here. We're going to leave it at 6 standard deviations from the background, which is probably this dark color, or at least maybe a little brighter than the dark color, right? And this one's going to take a while to run, because if I remember right, this one finds around 4,000 objects. 17 full width half max. Now what we have to consider is it has probably calculated that massive cluster in the center is a single object. Okay, we all know that's not a single object. We all know that these, and even these large objects, that is probably, let's see if I can make this larger. Oh, you annoying son of a biscuit. Stop going to my other monitor. These large bright objects are obviously, these are probably stars based upon the diffraction of the light into those 4 points. I would guess these are stars. Now this weird shaped guy is probably a galaxy, right? Let's see if I can zoom in on that. Yeah, I think it's safe to say that that's probably a galaxy, right? That's right in the way of this image. And then, like I say, these guys are probably just stars that are much closer than the objects in the actual field. But what we need to do is we need to think about these things and allow change. We're going to go back to something like a 5 full width half max, because this image is comprised primarily of those small objects and around that cluster in the center. And then we're going to give them, we're going to bring these multipliers back just a smidge. Instead of 4, we're going to go 3. Instead of 8, we're going to go 6. And instead of 10, we're going to go 8. We're going to leave gain and readout noise as the default. Okay, so what you see is these error sigma clipping iterations exceeded. That happens when that inner and outer annulus includes a lot of light from nearby objects. Now, the good news is these are flying by quickly, meaning it's not... Once it hits 10 iterations on that sigma clip, it clips out outliers, and then resets, and then it clips out outliers again until the standard deviation only changes by, is it 1,000th? So if the iteration, the standard deviation only changes by 1,000th from the iteration before it stops. It's like, okay, this thing is clipped. We have removed outliers. But it keeps going until it gets outliers, and the standard deviation only changes a smidge. So we've got, here's our output, and it's still, why didn't it tell me how many objects it found? We're going to learn at the bottom of this one. 4,387 objects were found. Okay, and I'm sure it's probably still building the overlay, because that is not a fast. That overlay is a tool that will be optional. Yeah, they're dangerous, but these recursions are literally just checking values of 8 2D array. 8 values in a 2D array, and then it just recurses and does the same thing. It's not doing this huge. I once wrote a sorting algorithm in my CS330 class in Python that was recursive, and I didn't run it on the large dictionaries that they gave us. I run it on the smallest 2 or 3. The smallest 2 or 3 were like, I think the smallest one was like 10,000 words, but the largest were like 300,000 words. And on that big library, it took, I think, 20 hours for my algorithm to sort that big library. So tail recursion in Python is not really a great idea if you're going super deep. But in Java, thanks to garbage collection and other cool things, it's not too shabby. But let's see, is my overlay still being calculated? Nope, there it is. Okay, so this one's kind of fun too, right? Like, oh, you annoying sack of. All right, so I guess that's as large as it's going to let me display it, which I find to be wildly annoying. I wonder if I open this. It's opening these images with ImageJ, and I just can't figure out how to get it to fill the screen. But as you can see, it's finding lots of tiny objects out here. Let's see if any of them actually make sense, though. Not really, right? Like, it doesn't look like, I don't see anything around. There's nothing in the center of here. So I'm not entirely sure what the heck is going on here. Something super strange. Hey, I got one. There's one. But I don't know what's going on here. I don't know what's going on here. Needless to say, live data is not going well on my algorithm. On that easy to do stuff, that super simple no noise, everything evenly spaced. It's working well, but when the noise comes in, it's getting lost, and I gotta figure out why. So, anyway, back to let's go over a little bit of the code here, and then I gotta get to the office and get you guys on your way. Finding dark matter, maybe, yeah. Instead of intensity, it's looking for gravitational effect. That's what it is. Yeah, that's the sources of gravitation that all those nearby objects are speeding towards. I don't know. I'm just a computer scientist. I can make up astronomy as I go, I suppose. I just need astronomers to keep me in check. But anyway, let's talk about it. So, as I mentioned, let's get up here. Okay, so this is obviously the imports. That's not interesting. This is creating an object out of the FITS image that ImageJ can work with, an image processor, essentially. And then you can create, I created a 1D array called pixels from that image processor with a method called getPixels. And then I sorted one for one of the I think it was the median. The median needs to be sorted. So to get the median on the image, I created one to be sorted. And then down here, let's see. Let's see. Oh, okay. So I just I probably could literally just copy pixels into sorted pixels, something like this. Could probably do that instead of this. Let's comment this out. Oops. Where is there it is. Comment with block is Control-Shift/. So Control-Shift/. And then let's see here. Anyway, I don't know how I got so easily side. Okay, that is not working. That is not working. Am I right? Okay. So that caused problems. Let's Control-Z that a few times. Just had a thought to refactor there in the middle. So we generate the pixels, and then we just use an array sort method on that. And then we get the mean, median, and standard deviation of those arrays by passing them to these methods that I wrote. Generic dialog, that's that little box that pops up that asks how many standard deviations over the background that we want to choose. And then this is just a string array of the choices, that sort of thing. And then n sigma is what the input that we gather from that. Well, times the standard deviation. So we create a couple of, so here I created 2D arrays, so I didn't have to think in offsets, which is another refactoring that I'm going to do. But again, I was just trying to get some functionality going, but I wanted to create these 2D arrays. So here I didn't have to think in offsets, and I could just literally do a 4x or a 4y and then a 4x. So we start at the top first column, and then we go all the way across that row, and then let's see, am I doing that right? Is it x? Or maybe it is x and then y. Anyway, we created controlling width left to right, converting origin from TLC to BLC. Okay, so that's why top left corner to bottom left corner. I originally started at top left corner, but it turns out astronomers like the bottom left corner to be the origin of images because they think of the image as being in the first quadrant of a Cartesian plane. So I had to move that around. Okay, so here this get object is a large method that I wrote that runs that walk image method, runs that find nearby objects method, and essentially gathers up all these pixels that are brighter than the standard deviation, packs them into a class called unidentified object, and assigns all kinds of instance variables to it, including X coordinate, Y coordinate, center intensity, and all kinds of other stuff. Here is where, okay, and then that returns an array list of unidentified objects called UOS, unidentified objects, UOs, if you will. And then here, for each object in the unidentified objects array, we run a build fit, which essentially is a smoothing. It smooths the curve from, well, the build fit runs on both axes, so it'll smooth the Gaussian curves, and then it, the math is not coming to me right now, but it essentially generates the full width half max, is some fancy math for generating the full width half max on each object. And then what we do is we let's see, what are we doing here? We take it from each I can't even remember my own code. It's been so long that I wrote it. We take the average for each axes, and then we create an image full width half max. Is what's going on there. The temporary scanner was because of the GUI that I was designing. I was having too much trouble with, so we're taking our input from the console for now. And then here, let's see. Okay, so this is the stuff that starts gathering that input that I was putting in the console. So it let's see, and then here's where it asks for us to update that, and then it takes in that update. If we pass nothing, it's set as what it was calculated. If it's past something, then it just parses that as an integer into, and that shouldn't be an integer, that should be a float. I remember finding that yesterday and wanting to change it. And then here it sets the default aperture multiplier to 4. I'm starting to wonder why this is up here instead of after it checks to see if you're changing it, and that may be part of my bug too. But anyway, it says that it's caught here, that it's it asks if we want to change it. Oh, here it calculates it again if it's changed. Okay, all right. So that makes sense. Not entirely sure why I do that. I would think I would just determine what it is and then set that variable after this loop. But anyway, that's one of the things we as new developers learn the hard way. Yeah, Fenrir was telling me why my idea to just set that sorted pixels to equals. You're right. I was just creating a reference to that instead of actually creating a whole nother object. And dealing with Java variables by reference and value is not anywhere near as easy as it is in C++ and other languages where you just create a pointer, right? If you want to create a reference to an object, you create a pointer, and then that allows that object to be changed. Where if you just pass it by reference, it's just passing a copy to provide information that after changes are made, if they're even made, are discarded, right? Yeah. Okay. So anyway, here we're calculating the aperture radius, Then we're calculating the inner annulus multiplier and radius, outer annulus multiplier and radius. And then here's where the fun stuff gets to. It asks us about gain and readout noise. I just wonder if this readout noise is something that I should be putting that signal to noise ratio in, because when we determine that signal, it's using that value. But anyway, I'll have to double check with Andreas when I get back to the office. And then here is where it's outputting that the red will be the aperture, the green will be the inner annulus, and blue will be outer annulus. And then it spits out the number of objects found in the field, and then it creates the frame. Then it displays the output here. Let's see what's going on here. We're creating the array lists of the regions of interest to generate the overlay. And this is where we create the ovals. There is no circular region of interest in ImageJ, but it's fine. We just have to put the width and height and the parameters. And then here we're setting those parameters. And unfortunately, it creates the region of interest from the, I believe, top left instead of the center, which I find completely confusing, which is why we got the X center minus the radius, so I can move left by the radius, and then the Y center minus the radius, which will move it down. So maybe it's the top right corner, but anyway, and then we got the width and height or the diameter instead of the radius, so we multiply them times 2 naturally. And then we add the region of interest to that array list, set the color to red, and then we add the region of interest to the overlay, which is that image you see that pops up. These are the sort of things that will be optional and speed this thing up. If you don't want, if you're comfortable with the values that you put in, and you don't need to see them to see if those annuli are grabbing nearby objects or whatever, you don't need that, and it'll speed this up. And then it does that to the inner annulus and the outer annulus. And then here, what it does is those regions of interest include everything inside them, including everything inside of the regions of interest inside of them. So we have to subtract those regions of interest. We have to subtract the inner annulus from the outer annulus just to get that ring of pixels. And that's what's going on here. 4 points in the outer annulus. And here we have some edge detection going on. What I found was that ImageJ will create a region of interest even if it goes off the image, and it will give negative indices. Or indices that go beyond, if it's to the left, or if it goes off the bottom, it's a negative indice, and if it's to the top or right, it'll give something that's larger than the image. And if you try passing an array an index that doesn't belong, we all know what happens then. So what it's doing here is checking to make sure that the X value is greater than 0, the Y value is greater than or equal to 0, and the X value is less than the width, and the Y value is less than the height. And it's not less than or equal to, because we all know that array indexes start at 0 instead of 1. So it goes, these images are 2400 by 2400 pixels, so it goes from 0 to 2399. So if it makes it 2400, it's gone off the image. And that's essentially what it does here. Okay, so here it's adding. So it adds them all. And then here, for the points in the inner annulus, if the outer annulus contains points from the inner annulus, contains P from the inner annulus, then it removes that point. Here is what's going on there. And then we run that sigma clipped annulus, or we run that outer points array list that it had everything inside of that inner ring removed through this sigma clipped annulus, and then we pass it the canvas because it needs to be able to look at those intensities and check them against background, and then we run. We determine the median and the mean here, and then here we have a method to determine the mode. Assuming the median is larger than the mean, we run this method. If the median is smaller than the mean, we just use the mean. And then we calculate the background here, set the background on each object. Ooh, something weird just happened on my other screen, some flickering thing that about set my it almost triggered me. But anyway, and then here we are calculating signal by pulling the intensities out of the aperture. This is the aperture points. For each point in the aperture, we just iterate the signal. On signal, if there's a gain, we multiply it times the gain, and that is turning CCD values into electrons is essentially what's going on there. And then if the gain is not 1, then we just pull the value. Or if the gain is 1, I'm sorry. We're not going to multiply everything in an array by 1. That's just silly calculations that are unnecessary. And then we subtract that background. This is where we subtract that background from the signal. And then we set the signal, and then we calculate flux. This is that weird plus or minus that we take the square root of the signal time gain plus the outer annulus points, or the annulus, essentially the size, the number of pixels in that list, and then we multiply that times the background times gain plus the readout noise squared, and that's essentially the math and science. So now that I've been live for over an hour, the boss is probably wondering where I'm at, and I need to get going. So, and unless anybody has any questions, if anybody's interested in those images at all, just DM me, not CosmoQuest, DM me your email, and I'll drop these images in email to you. Or if it would be easier, I could probably just drop them in the weekly Space Hangout Slack if you guys are there. It would be easier. But I'll give you 30 seconds to get that done. And then, right on. Hiptacular Raptor. Dropping the 4,000 bits to feed science. We appreciate you. That's another great idea, DPI. I also have a blog that I've been trying to update weekly. It's been a couple of weeks since I updated it, but I could also probably post them there, which is my blog is just essentially, let's see, it's Big J to the Izzo at github.io, I believe, is the blog. Yep, there it is. You guys are welcome to go there, comment, let me know. Actually, if you could comment and remind me, I could drop those images there for you. And other than that, I'm going to go ahead and call it. Thanks again, Hiptacular Raptor. I'm going to let the boss lady know about your generosity when I get to the office. She will be greatly appreciative. We are having a farewell party for Ryan Owens. Friday's his last day, and I'm sure those bits will come in handy. We're going to go downstairs to that fantastic restaurant that the office is over. It's called Cleveland Heath, dopest restaurant in Edwardsville by far. And we're gonna have a couple cocktails and a few appetizers, and we're gonna bid our friend a fond farewell and wish him luck to his new gig. But meanwhile, I gotta get it back there so this cat can educate me on this Django/CosmoQuest project. So thanks again, everybody, for hanging out. It was awesome. I'll be back again Friday. I'm coming back Friday. Matt's still out of town Friday, so I'll be back Friday, and then I'll try to do what I did today much more quickly because I assume it's going to be primarily the same people. If you could scrape up some friends that are interested in astronomy or coding or anything at all, I'm happy to spend the whole time answering questions and none of it coding. We are trying to increase awareness. This isn't necessarily supposed to be a productive time for me. This is a time for us to grow awareness for the organization, for CosmoQuest, for the Astronomical Society of the Pacific, which and then for Pamela, which runs around all over the world gathering funding for us so we can do this cool stuff. So we're going to call it. You guys have a great day. We'll see you tomorrow for the daily daily space news, and then we'll see you again Friday for that and my Astro 101 stream. Take it easy, guys.